Hello everybody, I am happy to see you again. Today, we will talk about the other mechanism, cam-follower systems. Cam-follower systems are frequently used in all kinds of machines. For example, the valves in your automobile engine are opened by cams. Compared to liquids, cams are easier to design to give a specific output function, but they are much more difficult and expensive to make than liquids. This chapter will present the proper approach to designing a cam-follower system. I will introduce kinds of cam-follower systems and how to synthesize motion programs for the follow motion. Cam design usually requires two steps. The first step is to synthesize motion programs for the follower. We will talk about four curves for the motions: a line, parabola, harmonic curve, and the cycloidal curve, where we skip the general polynomial motion, since its derivation is similar to other curves. So, I suppose you can study for yourself if you need it. The second step is to generate the cam profile. We will have two methods, graphical and analytical method, to determine the cam profile. A cam is a mechanical device used to transmit motion to a follower by direct contact. The driver is called the cam, and the joinment member is called the follower. A familiar example is the camshaft of an automobile engine, where the cam drives the push rods to open and close the valve in the synchronization with the motion of the pistons. When it comes to transforming rotatory motion into linear actuation, there is likely no better mechanism than that of a cam and follower system. Cam and follower mechanisms are often used in engines repeated machining and other manufacturing applications. A cam consists of a rotation shaft with a non-regular shape used to induce the desired linear motion. The left video shows there is a ready cam that translates linear motion. And the right video is a rotary index driver. It is a cylindrical cam driver several pins to generate intermittent index rotation. This mechanism is usually applied in automatic tool exchange devices of machine tools. A general cam-follower system consists of three elements. There are cam and the follower and the means to constrain the follower against the cam. A cam is reciprocating, oscillating of rotating body that imparts reciprocating of oscillating motion to a second body, called the follower, with which it is contacted. There are several general ways of ensuring that the follower always contacts the cam. The first is to force the follower to remain against the cam. For example, we can use a spring like this, or weight and the gravity of the follower. The second way to ensure contact is by constraining the follower motion by geometry. Usually, it's possible only with roller followers. The constraint is done by adopting a groove cam A groove cam is described in the right figure. You can see the furrow moves along the groove path in the cam. A groove cam is basically two cams, one internal and the other one external, such that the roller contacts either surface depending on the force direction. In this type of cam, the tolerance on both cam surfaces and the roller must be very tight. The other way to ensure contact, it can be by using conjugate cams with oscillating roller furrows. The most general case is two cams. A main cam and the conjugate cam are fastened together. Two furrows attached to the same output shaft but offset to accommodate the two cams like this figure. The cam design must be such that the two furrows can maintain contact with the two cams at all times. In the design process, we must design first the main cam to meet the design demand. Then the second cam, a conjugate cam, is designed so that the second furrow maintains contact with it. Since the position of the second furrow will be known for every position of the first furrow, the envelope for the second cam is defined as soon as the first cam is designed. In the conjugate cam, the two rollers are preloaded against the two cams to ensure the high accuracy. The cam have lower constant strength than with a traditional spring-loaded cam. In the case of very special cam geometries, when the conjugate is the same as the main cam, so only a single cam is necessary. We call it a safe conjugate cam. However, this type is rarely used in industry. A furrow is characterized by its motion and by the geometry of the face that contacts the cam. The cam furrow motion may be either rotational or translational, and translating furrows can be either radial or offset. You see, the furrow surface can be flat or curved. This slide shows types of furrows based on surface in contact. Furrow surface can be either knife edge, roller, flat-faced, spherical. Actually, these geometries are all of the same class depending on the radius of curvature of the furrow face. Within the figure, the knife edge have a radius of curvature that is 0. The flat face have a radius of curvature that is infinite. And the general roller and the cylindrical furrows have a finite radius of curvature. Considering contact stress and wear happen between two surfaces, rollers are the best choice for furrows. For furrows based on type of motion, we can see one is an oscillating furrow. The cam continuous rotates that drives the furrow rotating at an oscillating angle. And another is translating furrow. Continuously rotating cams produce reciprocating linear motion of furrows. Types of furrows based on line of motion are radial and offset furrows. For radial furrows, the lines of movement of inline cam furrows pass through the centers of camshafts look like this. And this figure shows offset furrows. For this type, the lines of movement are offset from the centers of the camshafts. Disc of plane cams is a planar cam. Such cam has an irregular contour to impart a specific motion to the follower. The follower moves in a plane perpendicular to the axis of rotation of the camshaft and is held in contact with the cam by springs of gravity. In practice, a large number of different cam geometries are found. For example, offset front face translation follower, oscillating cylindrical face follower, radial cam and translating left edge follower, and radial two-loop cam and translating lower follower, and so on. The translating cam is a contour of grooved plane sliding on a guiding surface. The follower may oscillate in the left side or reciprocate in the right side. The contour of the shape of the groove will be determined by the specific motion of the follower. This slide shows types of special cams for your reference: cylindrical cam and oscillating roller follower, end of face cam and translating roller follower, yoke cam and translating roller follower, and so on. Let us talk more about the cylindrical cam. This cam has a groove cut along its cylindrical surface. The roller follows the groove, and the follower moves in a plane parallel to the axis of rotation of the cylinder. Cam mechanisms have some advantages and disadvantages. The advantages are by designing the appropriate cam profile. The follower can be arbitrarily expected to move. Its structure is simple, compact, and convenient to design. If the displacement program is appropriate, cam mechanisms can be used at high speeds, so they are widely used in automatic machine tools, light industrial machinery, textile machinery, printing machinery, food machinery, package machinery, mechatronic products, and so on. The disadvantages of the cam mechanism include for accuracy of cam profile is too high. It needs to be processed by CNC machine tool, so manufacturing is expensive. The point between the cam and the follower is in contact with the line, which is easy to wear and should only be used in occasions where the transmission force is not large. In practice, the roller follower is frequently used in industry because it has lower contact stress and wear than other types of followers. And the stroke of the follower should not be too large, otherwise the cam will become bulky.